Welcome to this VirtualLink presentation. We will start by a few words on a classical compilation and link of an executable file. We will then explain the Linux IPCs on the VirtualLink notion. We will finish by an example to show how it works in concrete terms. So, to create an executable file, you start with some source code, here represented as .h and .c files. C++ files are not represented here, but are a proper alternative. You need to compile the file to obtain object files. Then, you have a library build-up process which results in the creation of either a static library with a .a extension or a dynamic library with a .so extension. With additional static libraries, you can either build an executable from static libraries only, or a comparable executable, except that it would be smaller in size, using a combination of static and dynamic libraries. When you launch such an executable, the system will assemble in memory the needed dynamic libraries with a smaller executable file to produce what is going to be finally executed. Please note that a single function can only be present once in an executable. Here, we will take the example of a function called normDist for normal distribution computation. If you have a second library with a second function called also normDist, if you try to link together the previous libraries with the new one to make an executable, it will result into an error because the normDist function can only be present once in the libraries linked together. In conclusion, in a single executable, a function can only be present once, and the change of the underlying source code implies a discontinuity and the need for non-regression tests. Let's now look at the solution to allow the plug-and-play of a module and avoid the non-regression test. To do so, we will need to use IPCs, acronym for inter-process communication. Let's suppose we have two different libraries with two implementations of the normDist function. We also have additional communication libraries at our disposal. We can build two executables, one per library, each executable using one of the normDist functions. So executable A contains the normDist function of the left library, and executable B contains the normDist function of the right library. A central executable could then ask, depending on a user-defined processing scheme, to either executable A or B to execute their own normDist function and give back the result. To make the process communicate, you can either use TCPIP sockets. This is comparable to telephone, and this is the only solution in case the processes run on separate CPU, or, as an alternative, if the process runs on the same CPU, use a combination of shared memory and semaphores, represented here by green and red traffic lights, to sequence the call between the different processes. This architecture being in place, the central executable can now call two different normDist functions, one per executable. Let's now recap the various Linux IPCs. We talked about three inter-process communication techniques: TCPIP sockets, semaphores, and shared memory. Two additional IPCs exist: pipes between a process and its son, and signals that can be exchanged between any kind of process. We will now see how we can virtual link two modules. One is a Holland-wide short-term interest rate diffusion module, and the second is a zero-coupon interest rate stripper. First thing, we need to have several modules talking together on a shared memory segment. A module should be able to call back its caller to get additional information needed to do the job. And second, to get a modular architecture, different modules will need to be able to discuss together. So here, in our example, CPFL Recept 2, which is a central process, i.e. the Hemera process, needs a calibrated volatility surface. it will call the appropriate quantitative module depending on the processing scheme, here CPFL recept3, asking for the vol surface. That module will call back the caller, asking for the volatility surface definition on the market value of the caps and floor in the surface. The central module will send information back in XML format. Then, the quantitative module CPFL recept3 will ask the central module for a zero coupon curve label and pointer to be able to calibrate the diffusion process to the correct zero coupon strip. The central module will ask the processing scheme for A, the zero coupon curve label, and B, the quantitative executable to call to strip that curve. It will then launch and call that executable to obtain the curve pointer on the needed discount factors. The zero coupon curve stripper executable will give back the results to the Hemera executable. The Hemera executable will give back the message to the CPFL recept2 module. Finally, when the volatility surface is properly calibrated and the computation is finished, the quantitative module will send back through the shared memory segment the information in an XML format to the central process. In fact, step 2 and 3 will be repeated several times, as well as steps 5, 6, and 7. Please also note that it is possible and that we have implemented the capacity to have several layers of shared memory segments communication. You can have a master level communicating via a shared memory segment to executable that are at sub-level 1, and then one or several of those executables communicating through shared memory segments to lower levels executable. Last, a comment on non-regression tests. Please note that those are no longer needed in this type of architecture, because here you do not modify models, you add new models versions. In the processing scheme, you can then create a specific context to test the new added modules, leaving the production unchanged, and you can move gradually production models to at the proper pace to the new quantitative modules. In forwards, model upgrade becomes continuous. Thank you for your attention.